was a different way of getting to fundamental theorem of calculus 2. Okay, so start off with 5.3. Again, basic properties of integrals. Okay, and probably the most important of the ones that we had before was the one called linearity. So let me just write it up to remind us what that was. It says that if you have a sum, if you're taking the definite integral of a sum of functions, then you can either sum the functions first and then take the integral, or you can take the integrals first, right? And then sum them. Okay, so you can integration commutes with additions. How you read this? Integration commutes with addition. And then the second part of that was that if you have a function and you're multiplying that function by some number alpha, then again you can either multiply the function by the number first and then integrate, or you can integrate first and then take your multiple. Okay, so integration commutes with scalar multiplication. Okay, so scalar multiplication, to distinguish this from function multiplication, right? It's not true that if I have the integral of two functions, it's not true that I can say, oh, I multiply the functions first and then integrate, or I integrate and then multiply the values of those functions. That's actually not true. Okay, but you can if you're just scaling your function by some number, then it's okay to commute. Okay, so that was the most important one. It's sometimes, just for your knowledge, it's sometimes abbreviated like this. You put the two into one, and you say AF plus alpha f plus beta g of x dx is alpha f plus beta g. Beta becomes the integral of g. So you can sort of combine these two into one statement. This is also called linearity. It's, if you have this, then you have these two. If you have these two, then you have this. It's the same thing. Okay. Okay. So here are some deeper properties of the integral, but they're also pretty straightforward. First goes like this: that if you have two functions f and g which are integrable on AB, and you know that f of x is always less than or equal to g of x, then you can conclude something. What do you think you can conclude? What will be the conclusion? Sort of obviously. Elliot.
This is the integral of x is less than equal to the integral?
Yeah, the integral of f is going to be less than or equal to the integral of f on a to b is going to be less than or equal to the integral of g on a to b. Okay, so that's probably pretty obvious. The second one is a consequence of that. If f is integrable on AB, and the value of f is always greater than or equal to 0, then what? Then what? Yeah, Leanna.
The integral of f of x must be greater or equal to 0?
Yeah, then the integral is going to be greater than or equal to 0. So it's sort of obvious, I guess. A to b is going to be greater than 0. Right? And you see how that's a consequence of the first one, right? The first property says that if you have one function that's bigger than another, then that guy's integral is going to be the integral of the other. Right? The bigger one's integral is going to be bigger than the integral of the smaller one. Right? And here you're saying that you have a function that's bigger than 0, so the integral of f is going to be bigger than the integral of 0. The integral of 0 is just 0. Okay, so it's a consequence. That's why it's called a corollary. Okay. The purpose of these sorts of things is to, or at least one thing that you can use these for, is to get estimates of integrals. So, for example, if somebody says, what's the point of this? Is to get crude bounds. Getting crude bounds, crude estimates. Well, bounds is better. Okay, so obtaining on hard integrals. Okay, so for example, here's a problem in the text, number 33. They ask you to say something about this integral. Okay, the integral from 0 to 1 of the root of 1 plus 8x to the 5th. Okay. Can anybody tell me anything about this integral? Anything about the value of this integral? Edie, yes?
It's always positive.
It's always positive, great. Right, because you see that you're integrating this thing, right? And you're integrating over 0, 1, so at least you know it's positive. Can anyone do better than that? Can anyone say a bit more than that? Right? We're integrating this function. The function is bigger than 0, so we know that at least the integral is going to be bigger than 0. Can you say a bit more than that? Can you be more precise? Edie, yes?
It's bigger than 1.
It's bigger than 1?
Greater than or equal to 1.
Okay, greater than or equal to 1. Everyone see that? Right? Because the thing that you're integrating, the function, right? This function is bigger than or equal to 1, right? On our interval of interest, right? The function as x goes from 0 to 1, this is always bigger than or equal to 1, right? So we know that this integral is bigger than or equal to the integral of 1 over that interval, which gives you a value of 1. Okay, so we have at least this lower bound. Okay, so this is what you call a lower bound for the integral. Okay. And maybe you can do better than that, or maybe that's where you want to stop. What about? Can anybody say anything else? Is that all you can say? It's bigger than 1? No? Cynthia, what else can you say? Anything?
I don't know exactly.
You don't know, but you suspect by my tone of voice that there ought to be something more. Yeah, Leanna.
I don't know if this is right,
Yeah.
but that it's less than or equal to 3.
Less than or equal to 3, great. Right? You see that this function is an increasing function, right? This is an increasing function. 1 plus 8x to the 5th is increasing. If you take the square root of it, it's still increasing. And you see that, so it's increasing, so its biggest value is going to be at the right endpoint, right? And at the right endpoint, its value is going to be 1 plus 8, the square root of that, so that's 3. Right? So we know that this thing is less than or equal to 3, right? And so the integral is less than or equal to the integral of 3 between 0 and 1, which is 3. Okay. And if you could do, that maybe is you might be able to do better than that, but at least you get this rough estimate of what the integral is. Okay, so this is you know, maybe some sort of application of the theorem. Okay, any questions? Any questions on how to do that? Or okay, the next property. The next property is this. Okay. Suppose you have a function for which f and the absolute value of f are both integral on some interval. Then, can anyone guess the answer? Can anyone guess the conclusion? Anyone guess the conclusion? Hey, Rachel.
Would the integral of the absolute value of f be greater than or equal to the integral of f?
Okay. Yeah, so you know, and why do you say that?
Because all of the like negative parts of f would be positive, so there'd be like more area.
Okay, okay. So you know that, for example, or maybe you, to use the previous thing, you could say, well, look, I know that f is always, the absolute value of f is always bigger than f, right? So this guy is bigger, the integral of it is going to be bigger, right? Okay. But actually, you can do something a little bit better than that. How about this? If I look at the negative of that, if I look at negative f, that's also smaller than the absolute value of f, right? Right? Is that obvious? Right? Because I can negative the absolute value of something is always bigger than or equal to the value itself. Right? So if I take the absolute value of this, then I get the absolute value of negative f, but that's the same as the absolute value of f. Okay. So I actually also know that this is bigger than, it's not only bigger than this guy, it's also bigger than this guy. Right? So if I put those two together, what kind of conclusion do I have? Does anyone see what I can say? I can actually say that this sort of thing is true, right? Because I'm bigger than the integral. I'm bigger than the integral of this thing, and I'm also bigger than negative the integral of this thing, right? One of these is going to be, since I'm bigger than either of these, then I'm bigger than the absolute value, right? Because the absolute value is going to be one of these things. Right? Let me say it this way. If I know that I'm bigger than A and I'm bigger than negative A, then clearly I'm going to be bigger than the absolute value of A. Because what's the absolute value of A? It's either A or negative A. Right? The absolute value of A is either A or negative A. So if I'm bigger than A and I'm bigger than negative A, I must be bigger than the absolute value of A, because it's one of these. Which go?
So just to like clarify the difference between the two is that when you put the absolute value like on the integral itself, that means you're taking the absolute value of the integral, right? Mm-hmm. Okay, and the other one is you're taking just the absolute value of the x.
I'm taking the integral of the absolute value. The integral of the absolute value of the function. So the picture is like this. You have one function. You have your function f. Okay. And what we're saying is that the absolute value of the integral, if I take this integral and I take the absolute value of it, then that's going to be smaller than if I take the integral of the absolute value of the function. Right? So here is absolute value of f. Right? Absolute value of f. Well, that's going to be bigger. The integral of this guy is going to be bigger than then the absolute value of the integral this way. This is actually, does anyone recognize this? Does this remind you of anything? Does this remind anybody of anything? Suppose I have a bunch of areas. Some of them are negative and some of them are positive. Okay, so like A, B, C, D. And I say, I'm going to look at the sum of these areas, A plus B plus C plus D. And what I'm saying is that that's going to be less than or equal to the absolute value of A plus the absolute value of B plus the absolute value of C plus the absolute value of D. I say that the absolute value of that sum is less than the sum of the absolute values. What's that? This should be familiar to you. The absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Does anyone remember the name of it? You know, maybe you don't remember the name.
Triangle.
The triangle inequality, right? This is the triangle inequality. So this thing here is some sort of, it's what we call, it's also called the triangle inequality. It's the triangle inequality, just the infinite triangle inequality. Okay, so again, these are things that you can use for getting bounds. In the field of math called analysis, a lot of what one does is try to get control of things. So you have some function, and you try to control like the size of the integral of that function. And this is a pretty common trick, the triangle inequality. You say, well, I don't know how to control the function. I don't know how to control the function itself, but when I take the absolute values of it, I actually can control it. And then you control this thing, and you say, okay, I get some control on it, which, since by the triangle inequality, gives me control of this smaller guy. Yeah. I have a friend who so the triangle inequality is actually something that a mathematician uses all the time. It's like a common tool, strangely. Yeah, I have a friend who says that the triangle inequality is the fact that the mathematical fact that he hates the most in all mathematics. And he's an analyst too, but he's always concerned with getting the exact answer. And every time you go to the triangle inequality, you're saying, I give up on getting the exact answer. So it's like defeatism for him. It's a symbol of defeatism. Okay. But for most people, we use it happily. And as long as we can get some result, that's great. Yeah. He's interested in what are called sharp results, like the absolute best result possible. Yeah, it's true. Once you use the triangle inequality, you've given up. Okay. Okay, the last thing we're going to mention today is the mean value theorem. It's the mean value theorem for integrals. Okay. It goes like this. If f is continuous on AB, then there exists a point C in AB where f of C equals the integral of f from A to B over 1 over B minus A. I'm sorry, times 1 over B minus A. we're not going to prove this. We're not going to prove this yet. There is a proof given in the book using the intermediate value theorem, and it's a nice one. But once we do the fundamental theorem of calculus 1, there'll be an even nicer way of seeing this. Okay, but so we'll prove later, shortly later. Okay. Okay, so let's at this point, all I want to do is talk about the interpretation of this. Okay. F is continuous on AB, right? So you have some interval AB, and you have some function F, and it's continuous. Then there's some point where f of c equals this thing on the right. Okay. Now, what is this thing on the right? What is this thing on the right? Can anyone tell me what this means? What you've taken the integral from a to b, and you've divided by b minus a. Can anyone figure out what? Can anyone make an interpretation of that? Edie.
Well, the area divided by that difference, it gives you a line. I mean, you're like the bottom times the height gives you the area, and now you're dividing by the bottom, so you're just getting a line.
That's right. Very good. That's great. So what you're getting, if I make a box with this height, let's call this height. So this height is okay. So here's the height. Let's take that's some number, right? What's the meaning of this number? Well, let's take a box with that height. What's the area of that box? Well, the area of that box is going to be this, right? Because base times height is going to be b minus a times 1 over b minus a times this integral here, right? So, in other words, what that is the height of a box that has the same area as under the curve that you were looking at. Right? In other words, this is the average value. The average value of f on AB. Right? It's the average value. If you somehow you said, well, I'm gonna think of this as water, and then just let the water settle down, right? The water would settle down to this height. Okay. The water would settle down to this height. It's the average value of the material. Average value of the function. Okay. And so what the mean value theorem is saying is that that if f is continuous on AB, then there is a point where you reach that mean value. There is a point where the mean value is attained. Right? So there is a point C where the average value, should say the mean value of f on AB is attained. So maybe that's a bit this mean value theorem. Maybe the name of it is even more appropriate. Okay. Any questions about that? Any questions about that? Questions? Right. You're taking the area under the curve, and then you're dividing by the width of the base. What you get is the height of a box that would have the same area. Right? You're getting the height of a box that would have the same area. You're taking the area under the curve, and you're dividing by the width of the base. Right? What you get is the height of a box that would have the same area as under the curve. Okay, so let's go on then to 5.4, fundamental theorem of calculus 1. This idea actually leads right into the fundamental theorem of calculus 1. Okay, so here it is. Let f be a continuous function on AB, and let capital F be the following function. So you make a new function. So you have one function. Oops. You have one function here on AB, and you make another function, capital F. So this one is little f. Capital F is going to be defined by taking the integral from a to x of the little function, of the original function. Okay. So in the picture here, if I want to know what capital F of x is, that will be this area here. Okay, so this is capital F of x. Right? This height here, of course, is little f of x. But capital F is the integral from a to x of little f. Okay. And I'm going to use a different dummy variable here. I'm not going to use x here because I'm using x for the bounded integration, and it's bad notation to use x in two different meanings. I don't want to call this the integral from a to x of f of x dx. That's slightly confusing. Although if you know what you're doing, it's not that confusing. But it's better not to do that. Because you don't know. It's not clear what the x is. Okay. Okay. So create this new function. Then capital F is differentiable. Is a differentiable function on AB, and its derivative is little f. In other words, capital F is an antiderivative of little f. Okay. So fundamental theorem of calculus is basically creation of antiderivatives. Right? Given any continuous function, it's possible to create an antiderivative by using the definite integral. Okay, so creation of antiderivatives. Okay, so earlier I said that e to the x squared doesn't have any simple antiderivative, right? You can't. What's the antiderivative of e to the x squared? You can try, but it's not going to happen. But you can make an antiderivative in this way. You could say, well, I'm going to make an antiderivative. Let f of x be the integral from 1, say, to x of e to the t squared dt. And that would be something whose derivative is e to the x. So that f prime of x is then e to the x squared.
I don't understand why you're changing the variables.
Well, I don't want to use x in two different senses.
Well, why is there an x for the f prime of x equals e to the x squared?
Because f is a function of x. Big F is a function of x, so I'm going to differentiate it with respect to x. So T is just T is is what you're integrating over, right? X is the bound. You're integrating T from A to X. You're integrating T from A to X. Okay. Yeah, but I don't want to call this X and say I'm integrating X from A to X. That's just confusing. Okay. Any other questions? Clear? Okay. So okay, I think we have enough time to do the proof. So we'll do the proof, and then we'll take a class picture if we have time. Hopefully. Let's see. Okay. So here's the proof. Pick any x and any b. Then let's consider the limit of f of x plus h f of x plus h minus f of x over h as h goes to 0. So, okay, so we're trying to show that this guy actually is an antiderivative, right? Trying to show that this guy actually is an antiderivative. So let's see what its derivative is. Okay? So okay, well the derivative is this thing, right? The limit of f of x plus h minus f of x over h, and then you just translate. So well, that's going to be the integral, right? Capital F of x plus h is the integral of little f from a to x plus h. Capital F of x is the integral from a to x of f. Right? And you're going to divide this thing by h. Okay. Now, what is this? The integral from a to x plus h minus the integral from a to x. What is that? Can anyone tell me? The integral of little f from a to x plus h minus the integral from a to x. It'll be the integral from x to x plus h, right? Because you're taking this area minus this area, right? So just by the properties of the integral, right, you get the integral of x to x plus h of little f, and you divide that by h, right? Okay. 2 points on the final. To anybody who can tell me what happens to this thing with some reasoning. Eliza.
Wait, we're talking about what happens to the integral?
What happens to this limit? Right? You're taking the integral of f from x to x plus h, dividing by h, and you're letting h go to 0. Rachel.
Okay, this isn't what you're looking for, but that looks a lot like the mean value theorem thing you just did for integrals.
Okay. So this looks like that's a pretty good start. Looks like the mean value, right? Looks like the mean value of f on x plus h. Ellie.
Does the integral, I don't know about the 1 over h, but does the integral part go to 0 because of the x to x thing?
It does go to 0, but we're dividing by something that also goes to 0.
I don't know.
Anything to do with E?
Nope. Samantha?
I also think it goes to 0, but because the whole h thing, it cancels out, but then when you divide over 1 over 0, you either get infinity positive or infinity negative or 0.
Well, who knows what happens when you get something that goes to 0 over something that goes to 0. You know, one way, yes.
Wait,
Okay.
is it actually 1 if we go at the same rate towards 0?
You guys are getting farther and farther. We got this tract. You got this tract. Okay. So, sorry. Bonus round is over. Look at, so you have this thing, x plus h, right? You have the function here, and x plus h shrinks in. Right? H is shrinking in, and you're dividing by the width, right? You're dividing by the width. So this is the average value, right? This is the average value of this thing here is the average value, the mean value of f on x plus h. Right? This thing here is that. Right? And then when h gets smaller and smaller, what happens to that mean value? Becomes very close to f of x. Becomes close to f of x. It turns into f of x. Right? Because your function is continuous, and as you take smaller and smaller intervals, you see that the average value is gonna get closer and closer to f of x. I'll give you 1 point for that, Rachel. Okay, so you got f of x, and that's the end, right? This function's derivative, this function is differentiable, and lo and behold, its derivative is f of x. Next time we'll see how fundamental theorem of calculus 1 gives you fundamental theorem of calculus 2 immediately.